Why differentiability matters? See, 3D Gaussian splatting is not just rendering. Okay, so see, the idea is that when we are doing the 3D Gaussian splatting, we are not just throwing some random, like uh, thousands of random 3D Gaussians on the screen. With that, some scene we will get, but the rendered image will be not the one which we are looking at. So there is a scope of optimization. So 3D Gaussian splatting is not just about rendering, it is also an optimization process wherein we will be training the Gaussians. Training the Gaussians means we will be learning the parameters so that the rendered image matches the real photos. And that is what is optimization is. Now it's very clear that if I talk about optimization process in 3D Gaussian splatting, it means for every 3D Gaussian, I will be learning the parameters, the position, the mu, the center, the covariance, the opacity and the spherical harmonics, the colors of every 3D Gaussian. I will be learning that so that for millions of Gaussians, if they are thrown at the scene, the rendered image is the one which will match the real image. And when I will be training, it will require gradients. Training will require gradients. So there is a concept of loss. So loss is basically the difference between the rendered image and the real image. And to optimize the parameters, I have to minimize the loss. So to optimize the parameters, we have to find the change of loss with respect to Gaussian parameters. So we call it the gradient. So this is the gradient. Gradient is the del L by del Gaussian parameters. So like how the loss is getting affected by tweaking the parameters. And if tweaking a particular parameter, the loss is getting reduced, it means I am on the right direction. I'll keep on decreasing it. So this tweaking or this gradient, it is also telling us in which direction we should move. Either we should increase or decrease the values of the parameters. So now it's very clear that, okay, optimization means minimizing the loss. What is the loss? Loss is the difference between the rendered image and the target image, the real image. The difference between the rendered image and the real image is the loss. The goal is to minimize the loss. So what we will do, we will calculate the gradient. And the gradients here will be how the loss is getting affected by changing the Gaussian parameter. The change of loss with respect to the Gaussian parameter. When we tweak the Gaussian parameters, the loss will get tweaked. The loss will change. So here we will get the direction. Like like if we want to increase a parameter or decrease, and this we will be doing for all the 3D, like every 3D Gaussian, this will calculate. And now these gradients, uh, it will flow through projection, covariance transform, blending, and shading. The idea is that, see, what will happen is that when we will tube the parameters, the effect of it will flow through uh, these steps. Because rendering pipeline we already discussed, we start with 3D Gaussians. Now I tweak the parameters, so I change the 3D Gaussian a bit. Because of that, projection will get affected, covariance transform will get affected, blending will get affected, shading will get affected, and the real image, the rendered image will get affected. And we have to keep on affecting it until it looks very similar to the real image, until the loss is minimized. So that's the idea. And now the goal is to have a fully differentiable pipeline. The Because the idea is that in every stage I'll be calculating the gradients. It's not like the idea is that I started with a 3D Gaussian. In projection stage, I'll be calculating the gradient. In covariance transform I did, I'll calculate the gradient. Blending I did, I'll calculate the gradient. Shading I did, I'll calculate the gradient. So I want fully differentiable pipeline wherein at every stage I should be able to calculate the gradient. So it should be differentiable. So projection is differentiable. Yes. Covariance transform. We already saw that when we will be doing the projection means 3D to 2D conversion. We will be projecting the center mu. That is the projection. That's like a straightforward mathematical transformation. It is differentiable. Covariance transform, we saw that we cannot directly be using the covariance matrix. Rather, we will be breaking it into scale matrix and rotation matrix. Now they are differentiable. So covariance transform is differentiable. Rasterization, it is differentiable. Because in rasterization, what I'll be doing is that I'll be doing the first term cooling and then dividing the scene into tiles and splatting the three Gaussians onto the screen. So that is the rasterization. Now this rasterization, it is like the multiplication of the uh, real 3D Gaussian with the view and the projection matrix, view matrix, and this is differentiable. And then we'll do the blending. In blending that the accumulated color equation we saw, that is also differentiable. So the pipeline, the rendering pipeline, it is fully differentiable, and that we need because at every stage, I will be calculating the gradients to learn. Now, see, one very important observation, like rasterization, it is usually discrete because in rasterization, what we are doing is that we are rendering the pixels. Rasterization is like a rendering. We are rendering the pixels. So traditional rasterization, since pixels are involved, it is discrete. Like it is like a pixel coverage test, whether that region will contain pixel or not. So it can be discrete. It can have sharp edges. So we will be doing something called as smooth or soft rasterization. So in soft rasterization, we'll get continuous functions. We'll get Gaussian fall off, soft alpha blending, smooth kernels. So soft rasterization will make the rasterization smooth and hence it will be differentiable. And this makes rendering fully differentiable. So if we look at the gradient flow, so in the forward pass, we'll start with 3D Gaussians and in the rendering in the forward pass from 3D Gaussians, we'll splat it on the screen, on the scene, and we will get a rendered image. So that's the forward pass. Now using that rendered image, you will calculate the loss. We'll compare it with the real image, calculate the loss, compute the loss, and we will tweak the Gaussian parameters. We'll tweak the parameters for like all the 1 million Gaussians. We'll tweak the Gaussian parameters in the reverse direction. So in the backward pass, what we'll do is that we'll calculate the image error loss. Based on the loss, we'll start tweaking. We'll tweak the parameters and we'll go in the reverse direction, like from blending, rasterization, projection, like that. So once again, I'll tell you what is happening. We started with 3D Gaussian in the real world. We splatted it on the scene to get a rendered image. Now we'll compare that rendered image with the original image, we'll get the loss. Now once we get the loss, we'll go in the backward direction. Like we'll go to the blending stage and we'll try to minimize the loss. We'll calculate the gradient, we'll tweak the parameters. Like we will try to we'll calculate the rate of change of L with respect to Gaussian parameters. For that blending phase, whatever the formula is, we'll optimize that. Then we'll optimize the rasterization. Then the projection will optimize. Like that in the backward phase, we'll keep on doing it. Then once again, we'll do the forward pass. We'll get an image. Now the image we'll get, it will be more closer to the reality. And like that, we will do it thousands and tens of thousands of times. And finally, the rendered image will start looking very similar to the real image. The goal is to minimize the loss. And hence, differentiability is very important.